dou Ex by dou X plus dou Ey by dou Y plus dou Ez by dou Z is equal to rho by epsilon. Okay? Then, what is curl B? Curl B, so this is, these are vectors. Curl B is equal to, so the x component of this one, if I write, that will be, so just imagine that you have I cap, j cap, k cap, dou by dou x, dou by dou y, dou by dou z, bx, by, b. So the I component is dou by, dou bz by dou y minus dou by dou z minus 1 by c square into dou ex by dou t is equal to mu naught to jx. This is the second term. Third term is the component of j, which comes with a minus sign, so I write dou bx by dou z minus dou bz by dou x minus 1 by c square into dou ey by dou t is equal to mu naught into jy. The last one, dou by dou x minus dou bx by dou y minus 1 by c square into dou e by dou ez by dou t is equal to mu naught jz. Now, if I substitute mu naught here and write a mu naught here, what is 1 by mu naught and epsilon naught? C square. So this becomes mu naught c square into rho. So what I will do is I will write c into rho here and divide each component of electric field by c. Okay, is that equation correct? So I have a c square, one c, I am dividing each component here. Similarly, here also I will have one c here and one c I will put it here. C is a constant, so I can actually transform it in, just write it in this fashion. Now if you look at the right hand side, mu naught times 0, jx, jy, jz. So right hand side is like a 4 current density with mu naught as the coefficient. Now what will be on the left hand side? Now left hand side, if you see, in this case you have some components of this del mu. Okay. So you can see that. So how do I write it? Right hand side is mu naught j mu. So left hand side also should be a vector, 4 vector. But del mu is a 4 vector. and del mu when it is taking a derivative of, so we must write del mu of f mu nu, you will get mu naught into j mu. So this field tensor f mu nu is what we have to find out. So this f mu nu is called the field tensor. In order to find out what this is, we can ask what is for a fixed value of mu. For example, I said mu is equal to 0. Then I write dou 0 f00 plus dou 0 dou 1 f10 plus dou 2 f20 plus dou 3 f30 is equal to mu naught into j0. But what is j0? j0 is c times rho. So I am talking about this equation. So this corresponds to this equation. Okay. Now dou 0 is what? 1 by c times dou by dou t. So is there any term like that? There is no term like that. Correct? There is no one dou by dou t term in this. So this implies f00 is 0. What about dou 1? Dou 1 is dou by dou x term. So what is f10 term? f10 term is ex by c. Similarly, f20 is ey by c. And f30 is ez by c. f30 is ez by c. So I have completed this equation. Now if you take mu is equal to 1, then what happens? So essentially I have changed the row, fixed the column index. That means I have got the first column. Now I am going to second column. Second column I will use this equation. Okay, so maybe now it is easy to write down directly. First column is 0 ex by c, ey by c, ez by c. What about second column? Second column I have to use this. There is a j0 term, correct? So this is the j0 term here, and so j0 term is in this case minus minus ex by c and dou by dou x is 0, dou by dou y is dz and dou by dou z is minus dy. That is second column. So this is over. And here minus ey by c, dou by dou x is minus dz, this is 0, and this is dx. And this is minus ez by c, and dou by dou x is minus, this is dy dz, minus dz, dou by dou x is minus dz. last column, right? I think I was correcting it here. This one I have to take. Dou by dou x is dy. Dou by dou y is minus dx. And this is 0. So this is the field tensor. This is what you call as a mu. So you can see that these components are electric fields and these components are magnetic fields. So there are different components. So essentially, electromagnetic field is not a vector field but a tensor field. So this is the tensor component of the magnetic field. But there will be another tensor corresponding to two of the homogeneous equations, which you can also write. For example, if you write these two equations, so what is this one? Dou dx by dou x plus dou dy by dou y, dou dz by dou z is equal to 0. And curl of E, so it is, must consider Ex, Ey, Ez here. Then you will have dou dx, dou dy by dx minus dou e. So this one minus dou dy by dou z plus dou dx by dou g is equal to 0. And dou dx by dou z minus dou ez by dou x plus dou dy by dou t equals 0, and dou y by dou x minus dou x by dou y plus dou dz by dou t. So these are the homogeneous equations, and right hand side is 0. So we are going to have an equation like dou mu g mu is equal to 0. So this will be another field tensor. So this pair of field tensors, F mu and G mu, describe the electric field. So what is G mu? G mu is equal to. So how do we write it? Right hand side is 0 anyway. So here there is 0. So this is 0 dx dy vx dy dz. Second one, I will have to multiply in order to get this 1 by c throughout a 1 by c, so that I will put dx by c here, by c here, to be consistent with that notation. So c by c, because the right hand side is 0, I don't have any problem in multiplying it by 1 by c, so that this becomes del 0. So in the second case, I will have 1 by c dou by dou t, so I will have bx, and I will have, so dou by dou x has nothing, so that is 0. Dou by dou y has ez by c, and this is minus ey by c. And finally, here I will have by, and dou by dou x will have minus ez by c, and dou by dou, this will be 0, then this is ex by c. and this is Bz. This is Bz, and Ey by C minus Ex by C, and then 0. So you can see that exactly the time-like components are electric fields here, the time-like components are magnetic fields here, this body is electric field here, whereas this body is magnetic field here. So these two tensors, F mu and G mu, are called the field tensors. And these two equations together, that is, this equation and dou mu, G mu nu is equal to 0. These two equations together, where F is given by this and G is given by this is called the covariant form of Maxwell's equations. By nature, Maxwell's equations are invariant under Lorentz transformations. Even though that was, the equations were even before relativity was discovered, but Maxwell's equations are invariant under Lorentz transformations. So this is called the covariant form of Maxwell's equations.
So the second equation is required because only in charge source field.
No, the relation between electric and magnetic field will have all the four equations.
Second, G mu.
Yeah.
In the second class, dou mu, G mu also.
Yes. So that is covariant form of two homogeneous equations.
Yeah.
Source field equations. Any questions?
So then F mu nu, the dual space, can be constructed by changing the sign of the method.
Changing the sign of?
The first row, the first column. Suppose I want to compute the invariance of this F mu nu.
F mu nu and
F mu nu. So then how to construct F mu nu?
you want to do what? You want to write F mu nu and F mu nu like this?
Yes.
What is this one?
The second one is constructed by changing the sign.
Oh, so that is not really by changing the sign, because so you are asking this question. Suppose if you have F mu nu, how do I get this in terms of F mu, F alpha beta?
That is
Right? Since this is a second rank tensor, you must use a fourth rank tensor to lower the indices. So you must use some tensor which is a metric tensor in the fourth rank. Okay? So something like this, G alpha beta mu nu into F mu nu. So this will become F alpha beta. Okay, so usually that is very complicated. In the sense, okay, how to construct that metric such that this is done in a general tensor is something which I do not know. Maybe there is a way to do it. Maybe you have assumed that there are four vectors that are going inside, giving you a scalar. But in principle, it is possible to do that. But it's not simply changing the sign. Okay, so this is kind of how we use this tensor. See, what is the summary of this one is that this is the crux of relativistic electrodynamics or special relativity itself. The genesis of special relativity is the understanding that the electromagnetic field is a tensor field. Okay, so what are more fundamental is not electric and magnetic field vectors, these field tensors. If you understand these are field tensors, this question which Einstein had, that electric field appears to be magnetic field in some frames, is obvious, because it is like if you have a coordinate system, if you are only looking along the x-axis, you will see only x component. If you are only looking along the y-axis, you will see y component. So choosing a frame in which the particle is at rest is like viewing only one component of it. So you see only magnetic field or electric field, whatever the case may be. So this understanding comes only when you view it as a tensor field. Okay, so electric field and magnetic field. So each component of this tensor is defined at a point in the space. That way it becomes a tensor field. Okay, so this is the one physical instance where